Hello all. Let me start with a big thank you to EcoWell and LabMuffin for giving us this opportunity to speak at this e-summit. Today I'll be talking about innovation which Croda has brought to the personal care industry in the area of inorganic sun filters, which are also known as mineral sun filters. Before getting into the actual presentation, I would like to give you an overview of solar protection at Croda. Our development and manufacturing is mainly European based. The dispersions are made at our facility at Ditton, which is in northwest of England. Our titanium dioxide powders are mainly manufactured in Mevisa in Spain. And across our two facilities, we work very closely together to support our solar care customers. Our global synthesis team is based at Ditton in UK, and it is ably supported by our formulation and application specialists all across the Croda globe, working in various labs. It is very important to mention here that our sites are GMP certified. What does that mean? That means that our products are suitable for sale in US as APIs. So if you want to sell your product in US as a sunscreen, rest assured you can use our solar technologies for that. In addition to introducing solar care technologies, we also collaborate with Croda's global formulation network, which is supported by formulations in labs all across the world. To name few are Brazil, US, France. It's in South Africa, Korea, majority of Asia like Korea, China, Japan, to name few. And this allows us to cater to the region-specific formulation needs, and that kind of brings us close to our customers. We work with like customer projects, try to work on the briefs given by the customers. So this global formulation network definitely puts us close to our regional customers. Croda is committed to be the most sustainable supplier of innovative ingredients, and we are working towards our goal of becoming climate, land, and people positive by 2030. These are the areas where Croda's existence has positive positive impact on environment and society. And we seriously believe that it is much more than just doing less bad. We seriously feel that we can make a difference here. By 2030, we also aim to protect at least 60 million people annually from potentially developing skin cancer, which could be due to exposure to harmful UV rays. And we want to achieve that through use of our solar protection ingredients. Let us switch gears and look into the inorganic filters. Those are going to be titanium dioxide and zinc oxide. These two are quite unusual oxides. In a sense, they are capable of absorbing UV light, but at the same time, being particulates, they also scatter light. Both absorption and scattering, which are associated with these two inorganics, they are functions of wavelength of the light, the particle shape and the size of the particle, and also the refractive index, which tells you about the chemical nature of these inorganic particles. Let's take a quick look at particle scattering theory to get the better understanding. Scientists have used a computer me theory program to look at TiO2 hard spheres, which is a controlled and an ideal system. Me theory predicts that scattering will be maximized if the particles are around half the wavelength of the light. Theory also predicts that as particle size is increased, the scattering of the light is shifted to longer wavelengths. So based on this, it is observed that UV light is best scattered by the particles of around 150 nanometer diameter. And if you have TiO2 particles of 250 nanometers in diameter, they're very efficient at scattering the visible light. So by controlling the particle size, we are being able to minimize the scattering in the visible region, and thus we can control whitening of this product on the skin. So that kind of helps you give less whitening, more transparent product on the skin. These inorganic oxides, such as titanium dioxide and zinc oxide, they are crystalline materials with regular arrays of atoms, and this periodicity gives rise to materials' electric and optical properties. The resulting energy level for semiconductors is such that their outermost energy gap is similar to the energy of the UV light. This means that they are capable of absorbing light of energies higher or a wavelengths lower than this. So if you're looking at TiO2, this absorption edge is going to be 3.06 electron volts, which is equal to 405 nanometers. And if you're looking at zinc oxide, the gap is a little larger, that is at 3.23 EVs, giving the absorption edge of 385 nanometers. So both TiO2 and zinc oxide efficiently absorb in UV region. So when you combine the scattering and the absorption profiles, that will allow us to generate an attenuation plot for these metal oxides. The overall predictions of attenuation are shown here, demonstrating the benefit in transparency of going to the smaller particle sizes and showing the balance of protection offered in UVA and UV regions for different particle sizes. So if you have smaller particle size, you will have UVB protection, but there won't be any UVA protection. There won't be any attenuation in visible light, so there will be less whitening. Um, this is true for an ideal system of hard spheres, but we can use this knowledge to create a range of particle-sized powders with different size distributions. Croda offers a range of particles with modified properties. Our UV protection range is called Solable line, and we have four key product families within that. They are Clarus, Harmony, Spectra, and Micno. We also have particles with other protection-related properties. Optisol is for pollution protection and Infravel for air protection. But for today's presentation, we are going to focus on our Solable product line. On this slide, we present Croda's current titanium dioxide range, looking at the particle size by transmission electron microscopy and also with X-ray disc centrifuge technique. What we see here is Claris, yellow line, which is the smallest particle TiO2 we have, and it has very narrow particle size distribution. It is centered around 30 nanometers. It falls under our nano category. And if you look at the Spectra line, which is purple in color, which has large particle size TiO2 with broader distribution centered around 170 nanometers. So Spectra gives you broad spectrum coverage, but it also attenuates in visible light regions, so there is some whitening associated. Between Spectra and Claris, you would find Harmony, which is shown by green line. Harmony particle size is smaller than Spectra, but it is bigger than Claris. It is non-nano, but it is less whitening compared to Spectra, and still it is broad spectrum. Here we have the same range of titanium dioxide powders, but now we have displayed the attenuation profile covering the UV range and into visible range. It can be clearly seen that the larger particles have more UVA protection, but suffer from more visible scattering as predicted from mean scattering theory. Another point worth making here is that the spectra particle TiO2 is showing less scattering than Meade theory would have predicted. So this kind of highlights that B scattering is good basis for particle design, but the shape and morphology as well as the size can impact on final attenuation offered by the product. On these slides, we show how different particle sizes look on various skin types. We had looked at skin type 1, 3, and 5, and we used Soluble Claris, Harmony, and Spectra formulations to compare their whitening on the skin. As I had said earlier, Claris has the smallest particle size, whereas Spectra has the highest particle size. So depending on that, you can see there is difference in the whitening on the skin. To supplement that, we also looked at a TEM images for Claris and Spectra. Claris, again, on the right side, which has 30 nanometers particles distribution. Obviously, there are not too many bigger particles, larger particles, so scattered visible light. So the skin looks kind of it looks kind of transparent on the skin. On the other hand, solar spectra particle size was around 180 nanometers. So there are few large particles to scatter visible light, and then that kind of results into some whitening on the skin. Titanium dioxide used in personal care is invariably coated material. Most of the products have multi-layer coating, which is applied in stages. The base layer is usually an inorganic oxide and is there to reduce the photoactivity of the titanium dioxide crystal. The outer layers are present to modify the sensory feeling or the properties of the powder. These properties could be better skin feel, water resistance, and more. The coatings also allow more ease of formulating the particles and readily compatible with the range of emulsifiers and emollients. The high coating integrity is required to minimize the photoactivity and also to maximize the organic compatibility. I just want to highlight here how important different coating technologies are becoming in our market today. Uh, and is an area of focus innovation for Croda. Most of our established product ranges are based on alumina stearate coating, but we are developing the same core particles with other coatings such as silica. Uh, Silica in fact, it's not exactly new to our market, but we have seen an increased demand for silica by clean beauty brands who are concerned about chemical phobia of consumers and want to avoid the use of word alumina in their inky names. So, in fact, we would like to get some feedback on coatings. If you have any preference or if you are like if you have any concerns about particular coatings. Croda puts high emphasis on creating correct particle size for the application. It could be for true transparency or it could be for enhanced UVA performance. Optimization of particle size in our products is achieved through the dispersions of particles in oil and water carriers. Here, the carrier fluid is mixed with the defined charge of dispersing agent to form a premix. Once fully homogenized, the premix is milled using high energy bead mill. The bead mill acts to break down the larger agglomerates of powder to a suitable particle size, offering desired UV attenuation. The milling process is closely monitored by UVB spectroscopy and which is mainly to keep a tight check on the particle size. Commonly used dispersants are steric, electrostatic, and electrosteric. This slide shows the link between particle size and the UV attenuation. If you look at two lines in this slide, yellow and blue, yellow line represents the dispersion, blue line is the bulk powder. Dispersions, they have aggregates, so smaller particles, their particle size distribution is very tight compared to the bulk powder where they have agglomerates. And if you look at the UV attenuation, dispersions tend to have high extinction coefficient and extinction coefficient in UVB region and minimal attenuation in UVB and visible region compared to the like bulk powders where they attenuate mainly in UVA and way deeper into visible light region, making them more white on the skin. Dispersion optimization is the key. The level of the dispersant is crucial in any colloid system. The solid loading and the dispersant concentration have direct effect on the rheology of the system. Commonly, thixotropic gel is preferred as a dispersion because on standing, the gel structure forms, it stabilizes the system, making sure that particles cannot aggregate. But at the same time, with small amount of shear, the system becomes free-flowing, allowing the ease of use, or also makes it easy for pumping into the manufacturing tanks. The dispersions which you see here are produced at 30% solids so that they could be prepared on bead meal and their UV attenuation profile or properties can be compared. The unmilled dispersions seen by the orange line is without any dispersant and it appears very fluid, but UV measurement reveals poor attenuation properties. Solid particles quickly settle out of the suspension to form sediment at the bottom, thus affecting its efficacy. When a dispersion with 3% dispersant is milled, uh, look at the yellow line. When you submit it to milling, UV attenuation profile improves along with an increase in the viscosity. The aggregates are now broken into constituent particles because of the milling. When dispersion is further increased to 6%, the light blue line on the slide, this allows the particles to disperse further and well stabilized. The UV properties are further developed, but when the dispersion is increased further to 9%, we see a spike in the viscosity. Even the UV properties are well developed, solid loading becomes limited. Recently, Croda launched a new zinc oxide in partnership with Intechno. It is called Solawell Micno Zinc Oxide. The particles have unique shape and they are ordered in a platelet-like structures. This results in less scattering and less reflection to the surface and thus gives unparalleled transparency on the skin when it is compared to the conventional zinc oxide, where visible light gets scattered back to the surface and thus giving a very white appearance on the skin. Micno zinc oxide is non-nano and it's available in powder as well as dispersion form. Next part of the presentation covers formulation fundamentals. In that, we are going to discuss importance of the film distribution on the skin, discuss the actives and phases where these actives are to be added. We'll also look at three most common types of mineral-only systems, which are comprised of titanium dioxide, zinc oxide, and combination of these two ingredients. So let's start with the importance of film distribution in sun care formulations. In order to achieve the high efficacy of sunscreen actives, it is important that the sunscreen is evenly distributed on the skin. It is very important, especially for the mineral sunscreens, as the efficacy is directly linked to the particle size and the distribution. Coherent film on the skin, even distribution of sunscreens, and optimal particle size ensures high efficacy of our formulation. This image represents the even distribution of actives within the film when the sunscreen produces an even film on the skin. So this is more like an ideal world scenario. In reality, we have bigger challenges. So how does it work in the real world? The uneven nature of the skin surface makes it very difficult to achieve such an even distribution. And in most sunscreen products, the true situation is likely to be closer to what we see in this image, with some parts of the skin surface having very little or no protection at all. A thin film model shows that these gaps contribute to almost 10% of the total skin area. What does that mean? It means that in the real world, 10% of the skin will be uncovered. And this is why formulating sunscreen is so challenging. This slide gives an idea about poor distribution of actives. The image which you see here uh, tells you what happens when an oil and water emulsion is applied and water phase evaporates under dry down conditions and oil film is left behind. The actives are poorly distributed on the skin. You see there on the slide. Some you can also see some agglomeration is occurring with the actives. Those are excluded from the oil film and they are staying on the surface. And in addition, you also see that some oil pools are being created within the skin wrinkles. So overall, if you look at it, it's a very poor distribution of actives. So when you have poor distribution of your actives, obviously you're going to have a very poor efficacy from these actives. And why is that? Because oil film is not continuous. So it is leaving those holes, leaving some part of the skin without any protection. Distribution of active particles is inconsistent. So some part of skin is getting this active, some part is not getting active. And and there is a possibility that some of the actives are not even being included in the oil film. So they are without any dispersing media and they are just forming aggregates on the skin. So overall, your efficacy is impacted. The product film composition largely depends on the type of emulsion you're working on. If it is water and oil emulsion, evaporation of water is very slow. So the film can be considered as consisting of the emulsion itself. If you're working on oil in water emulsion, obviously more rapid evaporation of water. So film will consist of oils, emulsifiers, actives, and other non-volatile ingredients present in the oil phase. In either case, it is very important that the film should be continuous and even as possible. And it is that to achieve even film it depends highly on rheology of the product. So we are going to see that in our next slide. As the right film also depends on the product rheology, it is required that the sunscreen has a low viscosity under high shear conditions, mainly to give good initial coverage of the skin. Then it should have a short recovery time after spreading to maintain the even film on the skin, and prevent the product from continuing to flow and pooling into the skin wrinkles. In oil and water emulsions, the composition of the emulsion and the rheology, they are constantly changing while the product is being applied. So oil droplets should ideally coalesce quickly to form the film. So that's the requirement. Let's move on to actives and find out where we should be adding these actives in our sun care formulations. Croda has range of dispersions available with different carrier fluids. So based on your carrier fluids and type of emulsion you are trying to put together, these actives can be included in either internal phase or the external phase of your emulsion, or can go in both the phases. The most versatile systems tend to have the actives in their external phase. If you are working with water-based dispersions, then they will be more suited for the water phase of oil in water emulsions. And if you have oil-based dispersions, then they will be more suited to the oil phase of water in oil emulsions. So you can always have them in both the phases to achieve the synergy, and that way you can have higher loading of solids if possible. Now moving on to the different types of actives which we can incorporate in the sun care formulation. Uh, to stay within the scope of this presentation, we are going to focus only on mineral only systems. So the actives which we are looking at will be the systems put together with either zinc oxide only or TiO2 only, or combination of zinc oxide and titanium dioxide. So let's start with titanium dioxide system. If you are working on a system where titanium dioxide is the single UV filter available in the system, in that case you will need to use titanium dioxide with improved UVA protection to meet the global UVA regulations. And for that purpose, you'll be using either soluble Spextra or soluble Harmony, which tend to have both UVB and UVA protection. If you happen to have TiO2 without UVA enhanced properties, then that's not going to meet UVA European regulations when it is just used by itself. If you are working with water-based dispersions of titanium dioxide, something like soluble XT40W, that will offer you great deal of flexibility while formulating, because soluble XT40W is a broad spectrum filter which will give you both UVB and UVA protection. So it can be the single UV filter you can use in the formulation. Being water-based dispersion, you can add this to your water phase of your oil in water emulsion. So your oil phase has a lot of room to add various different uh, oils to improve the feel of your formulation, or it will also allow you to solubilize other actives like other organic UV filters, and it will also make your Cosmos formulations way easier, and it will offer better spreadability, better skin feel, and will reduce the whitening appearance on the skin. If you prefer to work with titanium dioxide powders instead of the dispersions, yes, it can offer you benefit of lower cost compared to the dispersions. But to have a pre-dispersion made with homogenization or high shear equipment will be absolutely required to ensure the efficacy of the formulation. And if you are just working with TiO2 powders, then you will have to use either soluble XTP1 or soluble XTP2 powders, which will offer you broad spectrum coverage. Let's take a look at the systems where you combine zinc oxide and TiO2 together. Combination system is an ideal choice when you are trying to use more transparent TiO2 to improve the whitening properties of your formulation, but at the same time you need the broad spectrum coverage. But when you use transparent TiO2 which has lower particle size, it's not going to have enough UVA protection because it has high attenuation UVB region. So you will combine this TiO2 with zinc oxide, which has high attenuation in UVA region, but less attenuation, lower attenuation in UVB region. So when you combine these two, that's going to ensure a transparent product with broad spectrum coverage. Among the sunscreen formulations, emulsions are the most common form and the most popular form. They have the best rheology to form the good film on the skin. Also, they allow oily products to be applied in the uh, most elegant manner, allow incompatible ingredients and actives to be together. They can have them coexist. Since they contain a large amount of water, again, definitely cheaper option compared to anhydrous sunscreens, and also offer flexibility as viscosity, skin feel, and appearance, which can be easily modified. And now let's take a look at the system which is built with zinc oxide as the sole sun filter. It is always challenging to formulate with zinc oxide. If you're working with oil and water system, in that case, you might see pH drift and eventually leading to the separation. If you have zinc oxide system built with built-in water and oil, then you might see increase in the viscosity over the period of time. So anhydrous system could be the best option to work with zinc oxide, but it is not the most economical option. The most common problem faced by the formulators while working with zinc oxide system is the migration of zinc oxide. And it is evident by increasing pH. You will also see increase in electrolyte concentration. And there is a good chance that you'll see agglomeration of zinc oxide in water phase. So if you want to make a successful formulation, you must prevent this migration, and you should be able to enhance the redispersion of zinc oxide if it is uh, migrating, and also make sure that the system is tolerant to high electrolyte and high pH. And the most important thing is to control the pH, control the pH between 6.5 and 7.5. These are a few tips to make successful zinc oxide formulations, such as adding xanthan gum to water phase to ensure the redispersion of zinc oxide. Similar can be achieved by adding EDTA to the water phase. One can add propylene glycol to oil phase to redisperse the zinc oxide. Always maintain pH above 6 after mixing oil and water. So these are the tips which might give you a better chance at making stable zinc oxide formulation. Anhydrous systems are going to be the easiest ones to work with zinc oxide dispersions. Since there is no water phase, there is no scope for zinc oxide migration. Uh, as you see it in oil and water system, there won't be any thickening which you see with water and oil systems. They can be low viscosity fluids or high viscosity sticks based on your requirements. And since they are all anhydrous, they will offer good water resistance. Only downside is they are not going to be very economical option. While formulating your sunscreens, it's very important to look at the stability of the formulation. It's also really important to look at the SPF and UVA performance, look at the product sensory and the microscopy. Microscopy is not very commonly used, but it is a very powerful tool to predict the stability of your formulation. So before wrapping up my presentation, I would like to summarize few key points linked to the mineral-only sunscreen systems. Formulation of these systems guarantee simple and global filter systems, but again, they present certain formulation challenges. Key requirement is to maintain the good dispersion of particles in the emulsion and when applied to the skin. Use of non-ionic emulsifiers is the most preferred one for these filters. The most versatile systems tend to be those where active is in external phase. If you are working with water and oil systems, pay attention to the rheology of the system. And if you're working with zinc oxide in oil and water system, make sure that you are taking necessary steps to prevent the migration of zinc oxide to the water phase. And with this, I would like to conclude my presentation. I would like to thank you all for your attention. And again, big thank you for giving us an opportunity to present in this Sunscreen Summit. Thank you very much.